Welcome to the Professor's DuBois channel. This is Professor Corey. In this video is a mini lecture based on our third lecture covering material from Chapter 1. Disclaimer: this is in no way equivalent to our actual lecture where we discuss and practice the material in much more detail. We started this lecture talking about errors. Errors are not mistakes. Errors occur every time we make a measurement. Whenever you make a measurement, there will be some amount of error. If you weigh yourself on a broken balance and always weigh 10 pounds lighter than your actual weight, this would be considered systematic error. Random error may occur when reading a graduated cylinder. If your line of sight is not perfectly straight, you may estimate your last digit high or low. Lab reports will often ask for sources of error, so look to your measurements for error. Every measurement will have error. We can apply error to accuracy and precision. If we have low accuracy and low precision, like the upper left image, this would be an example of random error. The image in the upper right shows low accuracy and high precision. This would be an example of systematic error. We can minimize random error by doing multiple trials and taking an average. Systematic error may require adjustment to the measurement device. In the lab, instruments are routinely calibrated to reduce systematic error. Professor Victoria loves archery. How cool is that? Her accuracy is a little off, but her shooting is very precise. This is systematic error. If we move the sight on the bow, we should be able to improve the accuracy. Unit conversions are a big part of chemistry, and you will need to master this using a technique called dimensional analysis. If you have a different method, you should stop using it and start using dimensional analysis right away. We will use the term factor often. This term refers to a relationship between two units that are equal. For example, 1 hour equals 60 minutes. When we do these problems, we want to start with a number that is not a factor. For the first example, this is 1,575 donuts. We will make it a fraction by putting it over the number 1. To cancel donuts, you will have to multiply by a factor that has donuts. We will put donuts in the denominator. The factor in this example is 12 donuts equals 1 dozen. This was not provided, but it's expected that you would know this. The factor will be written as 1 dozen divided by 12 donuts. Then you simply cancel units and multiply. The third example given here is easiest if completed in 2 steps. Dimensional analysis is not just for chemistry. This is an example of calculating an annual salary based on an hourly wage. Notice that I started with something that was not a factor. 50 weeks only has 1 unit. I place this over 1. Then set up my fraction with weeks in the denominator to cancel this unit. My factor is 40 hours equals 1 week. I need one more step to get to dollars. Here is an example of a dimensional analysis problem taken from MindTap. First, I'll find the factors given in the problem, and if I find something that is not a factor, I will start there. In this case, the volume is simply 312 cubic centimeters, just 1 unit. I put this over 1 to make a fraction and multiply by a factor that contains cubic centimeters. By placing the cubic centimeters in the denominator, I am able to cancel these units. I want to make a mention here that density is a factor, and you will find problems involving density much easier if you use dimensional analysis. Thanks for watching. Please give this video a thumbs up and subscribe if you would like to see more mini lectures on the Professor's DuBois channel.